Hi guys, I'm Phoebe. Welcome back to my channel. In today's video, we're going to talk about 3 different formulas: present value of a growing annuity, present value of a perpetuity, and present value of a growing perpetuity. Before we start, let me have a question to help you better understand why we need these formulas. So if we are at year 0 and we are going to evaluate the present value of a project, we know this project will generate 100 million US dollar in year 1 and 100 million US dollar times 1.1 in year 2. We assume the growth rate is 10% per year, and in year 3 it will generate 100 million US dollar times 1.1 square. So what is the present value of this project? In today's video, we're going to learn all of these formulas. Let's get started. What is a growing annuity? Well, it is actually a series of payments that grows at constant rate G over time. So in year 1, we have cash flow C. In year 2, we have cash flow C multiply 1 plus G, as G is the growth rate here. In year 3, we'll have C multiplied by 1 plus G squared, and in year N, we'll have C multiply 1 plus G to the power of N minus 1 here. So if we are given a series of cash flows like this, how can we find the cash flow, the present value of cash flow in year 0? So instead of doing this one by one, discount each cash flow to the present value, we can actually do it in a more efficient way once we figure out the formula for this. So I'm going to derive this formula in order to help you have a better understanding of how can we reach this step. If you want to skip the proof part, you can go to this time directly. So how can we find the present value of this growing annuity? Well, the present value is sum of all the future cash flows discounted back to today's value. So for year 1, we know its cash flow is C. However, as we need to discount it back, so we need to divide it by 1 plus R, where R is the discount rate. We know that the value of $100 today is different from the value of $100 1 year later due to time value of money. So we need to discount this cash flow back to today's value. So for the cash flow in year 2, its cash flow is C times 1 plus G. However, we also need to discount it back to year 0. As there are 2 years, we need to divide it by 1 plus R squared. And for year 3, it should be C times 1 plus G squared divided by 1 plus R to the power of 3. There will be similar terms for the future years. And for year N, the last year, it should be C times 1 plus G to the power of N minus 1 divided by 1 plus R to the power of N. So we derive the formula like this. We'll call this formula our formula 1. And as we can see from this formula, there is actually a common term here, that is 1 plus G divided by 1 plus R. And we can see from here to here, it just multiplied by 1 plus G over 1 plus R. And from this formula to this formula, it just multiplies 1 plus G divided by 1 plus R, and so on. So this is called the common ratio. And we want to make use of this piece of information in order to help us make this calculation simpler. So what we'll do is multiply PV, this PV directly, by 1 plus G over 1 plus R. So this formula will be C1 plus G over 1 plus R squared plus C1 plus G squared over 1 plus R to the power of 3 plus dot dot dot, and the last term will become 1 plus G to the power of N divided by 1 plus R to the power of N plus 1. This term is equal to this term, and the third term here is equal to the second term here. And we'll see that the last term in the first formula is equal to the term before the last term. So a really simple calculation we can do is that if we do first the formula minus the second formula, the formula we can get is PV 1 minus 1 plus G 1 plus R is equal to C over 1 plus R minus C 1 plus G to the n to the power of n, C 1 plus R to the power of n plus 1, as all these terms are cancelled off. And here we get a relatively simple formula. It's just PV is equal to C divided by 1 plus R minus C 1 plus G to the power of n divided by 1 plus R to the power of n plus 1 divided by 1 minus 1 plus G divided by 1 plus R. So how can we simplify this formula? Well, we can move the common term out, that is C, and it becomes 1 divided by 1 plus R minus 1 plus G to the power of n, 1 plus R to the power of n plus 1 divided by 1 minus 1 plus G divided by 1 plus R. And as we can see, there is a common term, 1 plus R here, 1 plus R here, 1 plus R here. If we multiply 1 plus R on the denominator and the numerator, we can get C multiplied 1 minus 1 plus G to the power of n divided by 1 plus R to the power of n divided by 1 plus R minus 1 plus G, as we multiply 1 plus G on both sides. And now it becomes C divided by R minus G, as 1 here and 1 here cancelled off, times 1 minus 1 plus G, 1 plus R to the power of n. So this is same as the formula here. So let's have a really quick recap. So we first write an expression of PV, and then we multiply the common ratio on both sides. And so we'll get the same terms on the first formula and the second formula. Then we use first formula minus second formula to simplify this equation, and then we can find a simplified version of present value. Whenever I'm told something related to the growth rate, the discount rate, and the number of years, I can directly use this formula to find out what is the present value of the growing annuity. It offers us a relatively simple way to find the present value. Now let's have a look at an example. Suppose you receive $100 in year 1, growing at 3% annually for 5 years with discount rate of 7%. So instead of calculating each present value of future cash flow individually, you can directly plug these values into the formula. So present value is equal to cash flow 100 in year 1. Remember, it's in year 1. We shouldn't take some value in year 2 or in year 3. It's always in year 1. 100 divided by R here should be 7%, the discount rate, minus G, the growth rate, 3%, times 1 minus 1 plus 3% divided by 1 plus 7%, to the power of 5, as it grows for 5 years, and then we can directly calculate these to find the present value. So this is for our first formula. And our second formula is actually based on the first formula, the present value of a perpetuity. Now let's have a look at the second formula, present value of a perpetuity. So perpetuity is an infinite series of cash flow that continue forever. If we take a look at this example, it should be in year 1 the cash flow is C, in year 2 the cash flow is C, year 3 the cash flow is C, and it continues to infinity. For example, when valuing a company, we assume it will generate a cash flow, a yearly cash flow of like 100 million US dollar each year. It will continue forever, as this company is assumed to last forever. How can we calculate the present value in this case? Well, as we've already found the present value for the growing annuity, in this case we know n here, instead of being an integer, it goes to infinity. And here, in each year, the cash flow is the same, so the growth rate should be 0. If we simplify this formula, it should be PV equal to limit n goes to infinity. No worries, it's just a mathematical representation for n goes to infinity. So C divided by R, 1 minus 1 over R plus 1 plus R to the power of n. As n goes to infinity here, and we know 1 divided by 1 plus R is something smaller than 1, and we know this value, for example, it's 0.9 to the power of something infinity. If n goes to infinity, then the whole term here should be 0. So the value of 1 divided by 1 plus R to the power of n for n goes to infinity should be 0. And the present value, C over R multiplied by 1 is equal to C over R as calculated here. It makes our calculation much simpler. For example, if you receive $100 forever with a discount rate of 5%, the present value is just the cash flow, $100 divided by the discount rate, 5%. It should be 2,000. Not difficult at all, right? Now let's have a look at the last case. So the last case is the present value of a growing perpetuity. This time, instead of having fixed cash flow, each year the cash flow is multiplied by 1 plus g. So here it's 1 plus g to the power of 2, etc. And then as the cash flow is an infinite series, so in this case, we know n also goes to infinity, but g here is not equal to 0. In this case, we know there is assumption that g is smaller than r. So the whole term is a value greater than 0 and smaller than 1. And when its exponent is n and n goes to infinity, this value should goes to 0, right? So the present value is just PV equal to C divided by R minus G multiplied by 1 minus 0. Now let's have a look at an example. If you expect to receive 1,000 at the end of the first year, the payment grow at 2% annually forever, and the discount rate is 5%, you can directly use this formula. So the end of first year, receive 1,000 divided by the discount rate minus growth rate. Discount rate is 5%, growth rate is 2%, and as this is an infinite case, you'll just apply this formula and calculate its 1,000 divided by 3%. And you can put it in your calculator and find the answer directly. Now let's have a quick recap. When we are valuing a project or valuing a company, we first make sure if the cash flow is infinite or not. Yes and no. If it's not infinite, then we may apply the formula present value of growing annuity. And we may need to find the growth rate, the discount rate, and the year one cash flow. If it's infinity, we may need to find like if it's a perpetuity or a growing perpetuity. They're basically really similar. This is for g is equal to 0, and this is for g is not equal to 0. I guess this is the end of today's video. If you enjoyed today's video, don't forget to like my video and subscribe to my channel. See you in the next one. Bye!